Defines a formula. Defines a formula.
No, Cameron, you shush now. All right. Gentlemen, there is a website called falstad.com. It's an engineer that's made heaps of different applets and simulations to show wave phenomena and electrical fields, magnetic fields. This one's called the Ripple Tank. Now, we do actually have a Ripple Tank. It's a low depth water surface that you can create an oscillation, and you can see these waves. We will have that set up tomorrow. Thanks, Cam. I'll check that with IT and try and... Okay, I'll get it checked. So, shh, please. We are going to look at certain phenomena in this week and halfway through next week that waves do. And there's different experiments and different... you need to be able to explain all of the phenomena that waves can do. So we're going to treat our source as the disturbance. So if we go to our booklet now... Here is a very simple diagram of something causing a disturbance. Now, the easiest thing could be just a disturbance in a surface of water. So imagine you throw a pebble into a pond. That produces a disturbance which creates an oscillating amplitude. It could be a speaker creating sound waves. It could be a source of light producing light. But obviously, these wave fronts are going to travel off with a certain wave speed. That wave speed is unique to the medium. In this room right now, it's about 342. If it was light, it's 3 times 10 to the 8. If the disturbance is periodic, meaning it's occurring at a constant frequency, then every wavefront will travel a wavelength in the period of one wave. So basically I'm explaining V equals F lambda. If V is constant and F is constant, then lambda must also be a constant. Okay? Now, these are called wave fronts. Let's draw a few more wave fronts over... Oh dear, let's try that again. Close enough. Let's try and draw a few wave fronts. And once you get far enough away from your disturbance, you can treat your wavefronts as pretty much parallel, all right? That's what we do with light from the sun. It's so far away, and the object, I mean, it does have a certain apparent depth in the sky, an arc, if you were. We treat the wavefronts as coming into us parallel. Now, could we just identify that that is a wave front? Okay. Now, a wavefront is a region of common properties. It could be a region of the same pressure. Could be low pressure, could be high pressure. What are you doing? Where is your booklet? Where is your booklet? Huh? Well, yeah, but it doesn't mean you can sit there and do whatever you want. Get your booklet out. Get your booklet out. Close your laptop, get your booklet out. Come on. You don't have the book. I'm going to give you a spare one. Okay. So glad I had a spare booklet here. It's the same spec. I know. The wavefront, this could be common amplitude. So this blue line could represent a high amplitude of a surface water wave. It could represent a region of high electric field strength being produced by an EM wave. It could be high pressure from sound, okay? Now, we could then draw in the direction that this wavefront is travelling is obviously, since this is a transverse wave, the direction is transverse to that wavefront. We're going to call this a ray. All right, so you can draw waves as either wavefronts or you can draw them as rays, okay? The key thing is that the ray is always perpendicular to the wavefront, and the ray is showing you the direction that the wave is traveling. So, down here, pretty easy. Let's just draw this wavefront versus a ray. We're going to use these two ways of describing waves to describe certain phenomena. There's going to be a few that you need to be aware of and their definitions, and you need to be able to draw diagrams. I would say in revision for the test, there's going to be a lot of explanation questions. So you need to be able to know all of the different wave phenomena, so have their definitions. I would also suggest that you should be able to draw a diagram and also some common applications. Where do we see reflection? Where do we see dispersion? Where do we see diffraction? These are the things that we're going to learn over the next couple of lessons. Now, let me just quickly scroll ahead. Yeah, okay. There's something called Huygens principle. Now, this was back in the 1600s. Very early scientist. Each wavefront could be regarded as a source of spherical wavelets expanding from that point. But if there's so many of them occurring right next to each other, then you're not going to see any spherical waves because they're going to be combining together with each other. They're going to be interfering. I'm using certain wave phenomena that we haven't yet learnt. But Huygens' principle explains different phenomena using wave phenomena. Okay? Now, Huygens' principle can explain some interesting things. We are going to do this. We're going to take wavefronts and we're going to pass these waves through a small aperture. And what we will find is when the wave passes through that small aperture, the waves spread out in a spherical wave. I can show this, and I'm jumping ahead of myself, but since it's in the diagram and the booklet, I can show this using the Felstat app. If I go to single slit, now I'm going to clear the waves, stop it, clear, stop, clear. Why hasn't it started yet? Okay. Single slit. Oh, there it is. It just decided to start there. Let's stop that. Let's slow it down. So we're going to have wavefronts up the top, and there's a small slit just here, and we're going to pass the waves through, and the waves seem to spread out. All right, they don't just travel in a parallel column; they actually spread out, and this is Huygens' principle at work. That these wavefronts could be thought of as an infinite set of single point sources, and then when we get to the gap, the only point sources that are allowed to exist are those ones that are at the gap. So now we say, well, let's imagine those single point sources all lined up along that gap. They're going to then say, well, if you're a point source at that gap, you're going to spread out spherically. All right. So that kind of explains this phenomena. The second color scheme probably shows it a little bit better on the screen. The bright red and orange represents crests and troughs. Yes, Sam.
So the reason it doesn't spread out, if it's going in a circle, like a sphere, kind of like a ripple outwards, is almost like the circle's kind of holding each one end.
Well, we're going to look at this diagram here. The argument back then in the 16 and 1700s was whether light was a wave or whether it was a particle. If light was a particle, then we should find that if you just are firing a stream of bullets through a gap, the bullets should just keep travelling straight on. That's what the particle model would suggest. But the wave model suggests that once we get to here, Huygens' principle suggests that these wavelets would be allowed to propagate out spherically, and you should get the spreading of the wave. And sure enough, they were able to show this in the 1700s. The wavelength of light is tiny. It's about 10 to the negative 7 meters. And we'll learn about, there's a rule between the size of the gap and the wavelength. It basically has to be around about the same order of magnitude. So I'm jumping ahead of myself, but Huygens' principle is an important principle that helps explain certain phenomena. Over the page, let's go to one of the easy ones. You would have done this in year 9. It's damn easy. But I'm going to show this two different ways. Let's draw a wavefront first, and you'll see that a wavefront diagram is not the best way to draw this phenomena. Now, reflection is simply light bouncing off a surface not the best, and in fact I'm doing it very poor quality because if I try to draw a wavefront diagram to show reflection, it's getting a little bit jumbled up. Okay? So you don't have to take too much effort. Make it messy on purpose. I put my sad face there because a wavefront diagram is not the best way to show reflection, which is what waves can do. Apologies for jumping back to the Felstat app,
we have an applet that will show reflection. I hope. Internal. Where is it?
Oh, you're just going to pass it.
What is the phased array one?
Where?
The
Internal?
Is that right?
It's not really the one we want, but we can. Well, let's show it anyway. Here comes. Okay, look, wavefronts, wavefronts, wavefronts. They're approaching a surface where they're going to reflect. Ready? Can we really see what's happening here? Probably not until the incoming wavefronts oh, look. Right? Now, if I pause that at halfway, right, and we can set up the ripple tank tomorrow to show this phenomena. Right? If I paused it right now, oh crap! Would you be able to show? No, that's not really the best. You're not going to draw that on a test or an exam. What lends itself better is drawing a ray. So let's just add our ray to this diagram. I'm going to draw a line that's perpendicular to the wavefronts, travelling in the direction of motion, and I'm going to then bounce this sucker off that way, like so. Well, in Year 9, you would have learnt about Snell's law of reflection, that if a ray of light travels in at a certain angle to the normal, I know you've gone ahead, but it's in that yellow box above. It's the easiest law that you'll ever find. There's hardly any mathematics. The incident angle will equal the reflected angle when measured against the normal. Okay? Remember, the normal is perpendicular to the surface. I think we've done the normal to death when we looked at inclined planes and forces on surfaces. So, that's a good one. Light does that. Light will reflect, but particles also reflect. I'm sort of talking about Year 12. In Year 12, modern physics, in Term 3, we look at the conflict between the particle model advocates and the wave model advocates of light. But this could be for sound, this could be for light, this could be for water waves striking the surface of a harbour, okay, or a wall in a river. Now, refraction. We have the definition on the next page. Don't worry about the next page, but basically refraction. No, I said don't worry. The bending of waves as it passes into a medium of a different wave speed. Now, here I'm going to show you. Actually, turn over the page. I have changed my mind. The easiest way to explain refraction is to imagine a barrel that was rolling along a fast surface, such as concrete. All right? Now, the edge of the barrel would represent the wave front, and the direction that the barrel is rolling would be the ray. Okay? Now, I need you to imagine that if this barrel went from a fast-moving medium to a slow-moving medium, such as grass, since the wavefront has, the barrel has a certain dimension, it has a certain length. And what's going to occur is when this barrel reaches the boundary, the leading edge of the barrel now enters a medium where it's travelling slower. You need to visualise this, gentlemen. I need you to visualise that the leading edge is now travelling at a slower speed. The trailing edge is now travelling at a faster speed. And so you would find that when it crosses the boundary, it's rotating. And it's going to, I hope you can visualize that in your head, it's going to rotate this way, like so. Okay?
So wouldn't a better analogy be
No.
like a more
You could have the wheels of a car. Wheels of a car. A wheels of a car? A wheels of a car. Yes, exactly. Cameron mentioned the wheels of a car.
Yeah, that's such a good explanation.
The front wheel and the left wheel. Imagine you're a buggy and you're travelling from concrete to sand. That leading wheel catches the sand, it travels slower. And so the outside wheel is then going to turn.
Specifically designed not to do That was the highlight of the
Cameron, one more outburst from you and you will lose all talking privileges. We're going to draw rays to show the direction change. So here is my incident ray, which we can measure with an angle of incidence when measured against the normal. And then we're going to say, if we go from fast to slow, so I'm going to say V1 greater than V2. Okay, so it's slowing down. It was traveling from fast to slow. All you need to do is rotate your ruler towards the normal.
Did we learn the equation for how much it takes?
So there is an equation. It's not in the syllabus. You need to be able to draw diagrams and know which way it bends. I believe I've thrown in some extension questions that has Snell's law of refraction. Now, so let's just draw, this is for slowing down, it bends towards the normal. So I've got that sort of highlighted there. If the wave slows down, the ray, that's the key thing. The wave fronts don't really bend towards normal. It's the ray which shows the direction of the wave. Yes?
Then the wave is actually traveling slower. So
Yes.
So if
Yep.
light was to go through like something that was slow, the speed of light would be less.
Yes. And I will amaze you tomorrow with my laser beams, and I will bend them through mediums that have a higher refractive index. Back to our demonstration that has been politely stopped. There should be a refraction one. Tell me if you see it. There it is. Okay, here we go.
Did the double slip thing?
No. Yes. Okay. Now, here's my wavefronts. It just creates a disturbance with parallel waves. They're going to travel down to this medium. And we should be able to see whether it slows down or speeds up by which way it bends. Oh. So it slowed down and it bent towards the normal.
So some of it, like,
Less to more.
Yeah, some did reflect. And that's what happens. We know that light can do three things when it is incident upon a surface. It can pass through it, it can reflect off it, or it can be absorbed by it. And no surface can do exactly one thing. There's going to be a sort of ratio of some will be reflected, some will be absorbed. So this is just showing... Huh? Keep your radical ideas to yourself. So in that, I could have paused this. I don't know if there is a screenshot on your booklet. I don't think there is.
Why is there one moving away though?
Because some is reflected.
But like at the top.
Look, that's just the application just creates a disturbance, and
Yeah, it has to work with the same physics thing.
yes, it's using its own coding. So let's go the other way. I still want you to think of a barrel rolling, but now let's reverse it. Let's go from grass to concrete. Okay, so you can write it here: grass to concrete. And now, when the barrel reaches the boundary, the edge that enters is now travelling faster relative to the trailing edge that hasn't yet entered it. And so we would see that it rotates the other way. And we would find that our ray of light, when measured against the normal, has been bent away. So, again, there is an equation. We would need to know the properties of the two mediums to be able to calculate how much it bends by. But for now, you would just have to take your ruler and bend it the opposite way. Okay. So again, this would now be down here, this would be V1 is slower than V2, the wave speed. Okay. Now, over the page, rather than drawing rays, we're now going to try and draw wavefronts. So, first example, I'm going to go from fast to slow, please and thank you. In order to do this, I have to draw in a ray anyway. Let's just draw in a ray, smack bang in the middle, and your ray has to be obviously perpendicular. So make sure that that red line is perpendicular to the wavefronts. And then I'm just going to bend it, and we know that it bends towards the normal. So again, you can, if you want to, you can sketch in your normal if you want. It's just going to get in the way though. Now, here's the key thing. If you've drawn a ray that's bent towards the normal, when you draw the wavefronts, they just have to be perpendicular to that new ray. So if we bent the ray, we're going to have to bend the wavefronts. So, you just need to make sure with your ruler that you line up your, look at that, I've got some dashes on my ruler that's going to help me draw perpendicular wavefronts.
Could have remembered the angle you were drawing the first line at, and then you.
All right, Cam, you've lost your talking privileges.
Are you repeating my freedom of speech?
Yes.
Yes. There are certain things you can do in society. No, wait. There are certain things you can do in society, but then there are certain things that you shouldn't do in society. All right. Now, if you've drawn it correctly, you will notice something interesting. The wavelengths have dropped. If we looked here at our wavelength, call that lambda 1, our wavelengths have also decreased. And this is because of the wave equation V equals F lambda. And the key thing here is that your frequency will remain constant. It's a bit difficult to think, but imagine somebody was sitting here watching these waves pass by them, and they are counting how many waves per second. 1, 2, 3, 1, 2, 3, 1, 2, 3. They're counting 3 waves every second. That's all right. The frequency of that wave is 3 hertz. Now, let's allow this wave to diffract into a slower medium. And we have another person sitting here. All right? The application, the applet will show this as well. The person sitting here is going to count the same frequency. They're going to say 1, 2, 3, 1, 2, 3, the same frequency. But if it's traveling slower, then the wavelengths are going to have to be closer together in order for the frequency to match. One way to look at this is to say, since velocity is proportional to wavelength, if velocity goes down, then your wavelength goes down. We got 22 minutes left?
Yes.
All right, let's leave it there. Does anyone have any questions?
Oh.
Oh.
In one of the last tests, and just on the MSD stuff,
Oh.
it's always Y versus X. Yeah.
Yes.
Y versus X.
Yes. Let's pause it there. I don't want to, I want to give you guys the opportunity to do some revision for your SIS test. So we'll